Hey everybody, Mr. Covey here. We are talking about the equidistant theorems that you talked about in 4.4a, and this is the second part of that video, and we are going to build on what you talked about before. So first, we are going to look at the converse of what you talked about in the previous video. And this theorem says, if a point is equidistant from the endpoints of a line segment, then it lies on the perpendicular bisector of the segment. I'll draw a quick picture to make sure we're clear. So if you had a point A and it was equidistant, the same distance from 2 points B and C, then if you drew the perpendicular bisector to BC, you know that A would lie on that perpendicular bisector there. Are we going to use this for proofs? Good question. Yes, we definitely are. So let's look at this first proof here. So we are given a circle O. We are told that AD is the perpendicular bisector of BC, and we want to prove that AD contains O. Another way of saying this, what we're trying to prove here, is it's exactly the same as saying O lies on AD. So to show that O lies on the perpendicular bisector, we need to show that it is equidistant from the endpoints. In this case, the endpoints are B and C. So we're going to need to draw those two segments. Let's mark our given information. So if AD is the perpendicular bisector of BC, it bisects it, and it is perpendicular to it. We also know that since OB and OC are both radii of the same circle, they must be congruent. Okay, and now we're ready to go ahead and start our proof. Write down the given information, and then I will start the proof. Okay, so there's our given information. We also drew two line segments, so we need to say that. So draw BO and OC. Our reason, if 2 points, then they determine a line. Next, we know that BO and OC are congruent because they're radii of the same circle. So if a circle, then all radii are congruent. Spelled that wrong. Something important we need to state now is we need to actually say that O is equidistant from B and C. So we'll say that. It's important to include this step. And our reason is that reason from the previous video, if congruent segments, then equidistant. And now we've shown that O is equidistant from the endpoints of a perpendicular bisector. So using this converse theorem we now have, we can say that AD contains O. And the reason is this new reason. So if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. And we're done. This next proof's a little more involved. So let's go ahead and mark our diagram first. So we have that AC is perpendicular to BD. We have that AB is congruent to AD. And we have that angle 1 is congruent to angle 2. And this is angle 1. And this is angle 2. Okay, so what we're trying to prove is that P lies on AC. Like the last proof, in order to show that P lies on AC, we're going to show that AC is the perpendicular bisector of BD. And we're also going to show that P is equidistant from B and D. And then we're going to use this new theorem. So in order for P to be equidistant from B and D, we're going to want to show that those two segments are congruent. The way we're going to do that is by proving these two triangles congruent to start. Okay? Go ahead and write down the given information, and then we'll get started. Okay. So let's first take this perpendicular information and use that to say that these two angles are right angles. And in order to do that, we first need to say, or excuse me, we want to show that they're congruent. We first need to show that they're right angles. So let's go ahead and say angle 3 and angle 4 are right angles. Okay, so they're right angles because if perpendicular, then it forms right angles. Since they're both right angles, they're congruent. So now we have that 3 and 4 are congruent. We also, looking at our triangles, are going to want to mark PC congruent to PC by reflexive property. So let's add that down here. And now if you look at our picture, we can prove those triangles congruent by angle, angle, side. So let's go ahead and say triangle BCP is congruent to triangle DCP by angle, angle, side. And we need to state in there that we're using 3, 5, and 6. Okay, going back to our picture, we have those two triangles congruent. By CP/CTC, we can say those two segments must be congruent, which lets us say that P is equidistant from B and D. So let's come down here. That blue part was just to get the triangles congruent. Now we can say BP is congruent to PD by CP/CTC. Therefore, P is equidistant from B and D. Our reason is that one from that last video. If congruent segments, then equidistant. Now here's where you need to be careful. We've shown that P is equidistant from B and D, but we haven't yet shown that AC is a perpendicular bisector. So in order to show that AC is a perpendicular bisector, we need to show that it's a bisector and that it's perpendicular. We already have the perpendicular part. We need the bisector part. To do that, we use CP/CTC again to say, well, BC must be congruent to DC by CP/CTC. Therefore, AC bisects BD. For the reason that if two congruent segments, then it bisects. So now we have that AC bisects BD. We were given that it's perpendicular. So now we can say, putting those together, AC is the perpendicular bisector of BD. One other thing we should add here that we are using steps 1 and 11. Okay, so now we've shown that AC is the perpendicular bisector of BD. We've shown that P is equidistant from B and D, and that's enough to say that P lies on AC. And the reason for this is this new reason. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of that segment. And we should state that we're using 9, which is that it's equidistant, and 12, which is that AC is the perpendicular bisector. Okay, I want to introduce a related theorem which says that if a point lies on the angle bisector, so we're not talking about the perpendicular bisector anymore, we're talking about the angle bisector of an angle, then it is equidistant from the sides of the angle. The converse is also always true. So if a point is equidistant from the sides of an angle, then it lies on the angle bisector of that angle. Let's see how we use this in a proof. Go ahead and mark the givens and put your information, the given information, in your proof to start. Okay, so if we want to prove that angle 1 and angle 2 are congruent, what we're really trying to show is that AC is an angle bisector of angle BAD. And if we want to show it's an angle bisector, we can use this new theorem which says that AC will be an angle bisector provided that C is equidistant from the sides of that larger angle. And we actually already have that if you look. We have that C is equidistant from the sides of the angle. So right away we can say that. So C is equidistant from ray AB and ray AD. Our reason is if congruent segments, then equidistant. So since we know C is equidistant from those two rays, we can use our new theorem to say that AC bisects angle BAD. And the reason here is this new one, and it's if a point is equidistant from the sides of an angle, then it lies on the perpendicular bisector of that angle. Once we have that AC bisects angle BAD, we know then that angle 1 is congruent to angle 2. And we can just say if bisects, then two congruent angles. I want you to go ahead and do this proof on your own, and we will talk about it in class tomorrow. You're given that AW and AR are congruent. You're given that RF and FW are congruent, and you want to show that O is equidistant from AR and RF. And those are rays there. So go ahead and do that. Come into class, and we will discuss this proof. And that concludes 4.4b.